I'm going to talk about a project we've been working on over the past 2 years. It's called Glimpse. It's a system that tries to enable continuous object recognition in real time for mobile devices. And this is a collaboration work with my wonderful colleagues Lennon, Shul, Victor, and Harry. So people have been envisioning all kinds of continuous real-time recognition applications for decades. These kinds of applications locate where objects are in a video stream and overlay information related to the object in the view of a mobile camera. For example, a driver assistance application that locates and labels road signs to improve driver safety, and an AR shopping application which informs customers about the products they buy, and a face recognition application which helps users with cognitive impairment, and the tourist application which recognizes landmarks or buildings to improve user experience. However, despite the long quest for these kinds of continuous real-time recognition applications, today, current technology only provides picture-based object recognition, where a user takes a picture of a product or an object and waits for the picture to be processed. And after a while, he gets some information related to the item. Today, with the improvement of camera quality, the pervasiveness of wireless connectivity, and the emergence of wearable devices such as smart glass, we're envisioning a truly mobile video-based object recognition application, where you can simply wear your smart glass, walk around, and whenever you see something, it overlays information related to it in a glimpse. That's why we developed Glimpse. Its goal is to enable continuous real-time object recognition on mobile device in a video stream. So as a sequence of video frames comes in, Glimpse continuously identifies and locates objects in each frame. Before I dive into the details of Glimpse, I'd like to first explain how a typical object recognition pipeline works. It usually consists of 3 stages, and the input to the pipeline is an image or a frame. First, the detection phase searches a frame for objects of interest and locates them with bounding boxes. Then the feature extraction phase processes the content inside each bounding box to extract features. Then the classification phase converts feature vectors into labels using some machine learning algorithms, and the pipeline outputs the labels and the bounding boxes. This pipeline is general and long-standing. Even the very popular deep neural network still uses this architecture. In fact, developing a continuous object recognition application would be straightforward if the device had a capability to execute the entire recognition pipeline at a real-time rate of 30 frames per second, which is 33 milliseconds per frame. Unfortunately, the object recognition pipeline is computationally expensive and memory intensive and cannot be done on the phone within 33 milliseconds. Therefore, we need to look for places with larger computation capability. Servers in the cloud provide higher degrees of parallelism and better hardware capability compared to the mobile devices. And executing the entire pipeline in servers can be 700 times faster than executing it on the mobile devices or wearables. Besides, the hardness of the problem scales with the number of objects one wishes to recognize, and the classification model might be too big to fit into the memory. Therefore, we need to offload the recognition pipeline to more powerful servers in the cloud. This results in a client-server architecture designed for object recognition, where the server is responsible for the heavy lifting. The client captures frames from the camera at 30 frames per second, sends frames to the server for processing through the network. The server executes the entire recognition pipeline and outputs the labels and bounding boxes to the client. The client then renders the results on the display. Even though this design gives us some processing speed up, it also highlights 2 challenges. First, the first challenge is the end-to-end latency. The total end-to-end latency to process a frame is the network latency to process a frame plus the server processing delay. And when the latency is higher than the frame time, which is 33 milliseconds, it lowers object recognition accuracy. And the second challenge is the bandwidth and battery efficiency. Sending every frame to servers consumes too much bandwidth and energy. To solve these 2 problems, Glimpse introduces 2 techniques. First, an active cache design which combats end-to-end latency and regains recognition accuracy. Second, a trigger frame design which reduces bandwidth usage and resources consumed. Other papers such as Wishbone, Maui, Odessa, or Gabriel have proposed different ways to partition the recognition pipeline between the client and the server, or determine the partitions dynamically. But no matter what the partition is, they all share these two challenges, and Glimpse is the first work that addresses the performance degradation caused by end-to-end latency and tries to reduce the resources consumed. I will explain how Glimpse solved these two problems using the active cache and trigger frame design in the following slides. First, combating the end-to-end latency with an active cache design. I will use the following videos to demonstrate this problem. The left video shows what the user expects to see, and the right video shows what the user sees in reality when the end-to-end latency is higher than the frame time. Assuming it takes 1 second to process a frame, by the time the client receives the labels and bounding boxes for the previously processed frame, 30 frames have elapsed, and showing the results from 30 frames ago gives us bad recognition accuracy. To solve this problem, we ask ourselves, is it possible to combat end-to-end latency, relocate the bounding box without going through the server, and regain accuracy? Yes, it is possible if there are some fast operations that allows us to transform the position of the bounding box on the client. And this is where object tracking comes into picture. Tracking is a simple operation. It uses some points on the object and estimates where those points will be in another frame to relocate the moving object. This allows us to follow a moving object from one frame to another. What's even better is that tracking is faster than object recognition and can be done on the device within 33 milliseconds. So perhaps we can ask servers to return some feature points for the objects when returning the recognition results and run tracking from the previously processed frame to the current frame and relocate the object. Unfortunately, tracking is not perfect. It fails to work well when object displacement or the time gap between two frames becomes too large. This figure shows an example of tracking an object when the end-to-end delay is 1 second. Since the object has moved within a second, when we run tracking to relocate the object from frame 0 to frame 30, the tracking performance degrades. But since we know that tracking performs well when the object displacement is small, if we are able to ensure the movement or the displacement is small between frames, tracking can still be helpful. So our idea is to maintain an active cache of frames on the client to keep the displacement small and run tracking through the cache frames to catch up with the current one. This animation shows how active cache works when the end-to-end delay is 1 second or 30 frames. The client sends frame 0 to the server. And when the server is processing the frame, we cache subsequent frames in the active cache on the client. When the result comes back at frame 30, we have frame 0 to frame 30 in the active cache. We then run tracking through all the cache frames and reliably follow the movement of the object within that second. This technique works well when the delay is low. But when the delay is high, we might cache many frames, and since tracking is not free, running tracking through all the cache frames might take a long time. Sometimes it is even longer than the network plus the server processing delay. And we might again fail to catch up with the current frame. And to speed up the time it takes for digesting the active cache, instead of going through all the cache frames, maybe we should just process a subset of them. Luckily, it is possible to skip or subsample frames in the active cache because of the high temporal redundancy between video frames. By skipping too many frames, we might lose the benefit of maintaining an active cache. And as the network delay, the device capability, or the scene changes, it is non-trivial which frames we should select. Glimpse adaptive frame selection algorithm solves this problem, and here is the problem definition. Given n cache frames, select S percentage of frames out of n so that we can catch up without sacrificing tracking performance. Our algorithm achieves this by solving two problems. First, how many frames should we select? Second, which frames should we select? First problem, how many frames should we select? What is the number of S? The number of selected frames needs to strike the balance between the time it takes for digesting the active cache and the tracking accuracy. A smaller S allows us to quickly digest active cache, but might degrade performance because we lose the benefit of maintaining an active cache. And a bigger S ensures reliable tracking, but it takes more time, and we might again fail to catch up with the current frame. And the selection of S also depends on two factors. The first one is the end-to-end processing, which is reflected in the number of frames in the active cache. When the delay is low, we have fewer frames in the cache, and we can select a larger percentage of frames without degrading accuracy. And the second factor is the execution time of tracking algorithm on the client. The lower the client's computation capability, the longer it takes to run the tracking algorithm, so we can only process fewer cache frames. To obtain the optimal number of selected frames given different delay and device capability, we use a set of videos tagged with ground truth and simulate different end-to-end processing delay, tracking execution time, and the number of selected frames, and pick the S that maximizes the tracking, maximizes the accuracy. And you can see our simulation results in the paper. Then, given the number of cache frames we are allowed to process, which frames should we select? We exploit the fact that there's temporal redundancy between video frames and skip frames with no movement, and select those frames that capture object movement. To quantify the movement between frames, we use the frame differencing technique, which computes the per pixel differences as shown in this figure. We use the frame differencing technique because it is extremely cheap and fast and can be done on the device within 33 milliseconds. Then, given the amount of movement between frames, we select those S frames that capture as much movement as possible. And we formulate this as a dynamic programming problem, and you can read the paper for more detail. I will use these two videos to summarize the benefit of active cache. The left video and the right video show what the user sees before and after the active cache design. As you can see, having an active cache successfully hides the performance degradation caused by the end-to-end delay, relocates the outdated bounding box to the correct place, and achieves higher accuracy. Besides, the active cache has two really nice properties. First, the techniques used in active cache, such as tracking and frame differencing, are general techniques and can be applied to any objects. Second, no matter how one decides to partition the recognition pipeline and where the end-to-end delay happens, as long as the time it takes to process a frame is higher than the frame time, you can always use active cache design to hide the delay and improve accuracy. And the second challenge, the bandwidth and battery efficiency. Since sending every frame consumes too much bandwidth, can we send fewer frames without sacrificing accuracy? Glimpse addresses this challenge using a trigger frame design. In Glimpse, we compute trigger frames and strategically send only certain frames to the server to obtain the recognition results. We identify trigger frames using two techniques. First, we have to send a frame to obtain the recognition results when there are new objects coming to the scene. But however, running object detection on the client is expensive. Therefore, we can only approximate when there might be new objects appear. Therefore, we achieve this by measuring how much the scene has changed from the previously transmitted one by reusing the frame differencing techniques we used in the active cache design and trigger a transmission when there are too many significantly changing pixels. And the second one is to detect tracking failure. As shown in this figure, as the size, angle, or appearance of the objects changes, the track feature points will deviate from their correct location and degrade recognition accuracy. When this happens, the client needs to send the frame to the server to obtain a new set of feature points to track. We detect tracking failure using the observation that feature points of an object should have similar moving distance between frames. So we quantify the tracking performance using the standard deviation of distance of all track feature points between two frames and trigger a transmission when it becomes too large. And when the scene is constantly changing, the two heuristics might trigger many transmissions, causing a network or a server bottleneck. Therefore, Glimpse limits the number of in-flight frames sent to the server for which results are pending. Based on our experiments, having one frame in flight strikes the best balance between the bandwidth usage and the accuracy. So we evaluate Glimpse on two object recognition pipelines, the face recognition and the road sign recognition pipeline. We also collected two data sets to evaluate these two pipelines. For the face data set, we recorded 26 videos with the smartphone. In total, we have 30 minutes of video with 54,000 frames and 36,000 non-distinct faces. And the scenarios of the face data set include shopping with friends and waiting at a subway station. And for the road sign data set, we downloaded 4 walking videos recorded using Google Glass from YouTube. In total, we have 35 minutes of road sign videos, 60,000 frames and 5,000 non-distinct road signs. And to obtain the ground truth, we manually label the faces and road signs using bounding boxes. Our evaluation metric needs to take the location of the bounding box into consideration. Therefore, we use the intersection over union to measure the recognition performance. The IOU computes the area of the intersection of the detected bounding box and the ground truth bounding box divided by the area of their union. An IOU threshold of 50% is typically used in computer vision to determine whether a detection is correct or not. And this figure shows some example bounding boxes with IOU of 50%. And we say a detection is correct if IOU is larger than 50% and the label matches the ground truth. And we quantify the performance by measuring the precision and recall. The precision is defined as the ratio of the number of objects correctly labeled and located to the total number of objects detected by the scheme. And the recall is defined as the ratio of the number of objects correctly recognized to the total number of objects in the ground truth. And we evaluate Glimpse using 3 different network conditions, the Wi-Fi network, Verizon's LTE, and the AT&T's LTE network. So we will present our results as follows. We'll first talk about Glimpse accuracy and its bandwidth usage for continuous face recognition. And we'll show the performance of Glimpse for road sign recognition. And lastly, we'll show the performance of Glimpse when the device is equipped with hardware-assisted face detection. This figure compares the recognition accuracy of Glimpse with the server-only scheme. The server-only scheme directly outputs the results from the servers as they arrive, and it is used in other related work such as Gabriel. The y-axis shows the accuracy, the blue bar shows the precision, and the red bar shows the recall. For the face dataset using the Wi-Fi network, where the end-to-end delay is around 430 milliseconds, the server-only scheme only achieves precision and recall around 50%. With the active cache design, Glimpse improves accuracy by almost 2 times and achieves precision and recall around 90%. Using the trigger frames does not sacrifice the recognition accuracy and achieves precision and recall around 90%. And the black line shows the bandwidth usage, and the right y-axis shows the bandwidth usage in kilobits per second. With trigger frames, Glimpse reduces the bandwidth usage by almost 2 times. And we see similar trends under other network conditions as well. This figure shows the bandwidth usage for each video. The x-axis shows the video ID, and the y-axis shows the bandwidth usage. The blue and red line shows the bandwidth usage without and with the trigger frame design. As shown in this figure, Glimpse consistently reduces the bandwidth usage. And for certain videos, Glimpse provides as much as 60 times of savings. And for fast-moving objects such as road signs, the improvement is even more significant. Comparing to the server-only scheme, Glimpse improves accuracy by 71 times. Without Glimpse, continuous recognition is non-functional for the server-only scheme. And the recall is lower than the precision for Glimpse because road signs move fast, and we might miss some road signs when the dwell time of certain signs is shorter than the end-to-end delay, but the precision remains high. Similarly, using trigger frames reduces the bandwidth usage by almost 2 times and does not sacrifice the precision and recall. Some mobile devices are now equipped with object detection hardware, such as face detection. Is Glimpse still helpful in this case? To answer this question, we use our face recognition pipeline as an example. Since the recognition stage is expensive, we still need to offload it to the servers. Even with face detection hardware on the device, as shown in this graph, Glimpse still improves the recognition accuracy by almost 2 times. And this is because we still need to hide the latency of face detection at the client and the latency introduced by the server and the network. Having a detection hardware also helps reduce the bandwidth usage, since we can now only transmit the bounding box instead of the entire frame. As shown in this graph, Glimpse reduces the bandwidth usage by almost 2 times. And these results demonstrate that regardless of where the processing happens, if the processing incurs a delay, Glimpse hides it effectively using its active cache. And similarly, trigger frame enables the system to reduce the number of frames actually processed, thereby saving resources. To summarize, Glimpse enables continuous real-time object recognition on mobile devices, and Glimpse achieves high recognition accuracy by maintaining an active cache of frames on the client. And besides, Glimpse reduces the bandwidth consumption by strategically sending only certain trigger frames. To conclude, the performance degradation caused by end-to-end latency and excessive resource usage are 2 fundamental problems to object recognition applications. And Glimpse proposes the active cache and trigger frame design to solve these 2 problems. And these 2 techniques are generic and may be applied to a wide range of real-time vision-based systems. Advances in computing hardware and vision algorithm might change the placement of components in a system like Glimpse in the future. For instance, today, there's no hardware support on mobile devices for detection of objects other than faces, but that might change in the future. As long as the processing delay is higher than the frame time, the results will be stale by the time it is shown to the user. The active cache will hide the delay from the user, while trigger frames can reduce the number of frames that must be processed. Our experiments with Glimpse have shown that it achieves high precision and recall, reduces bandwidth usage, and outperforms other schemes. Thank you very much, and I'd like to take questions.